Anyway, I think I'll get started at this point. So I'm always trying to think of a topic that would be interesting to people. And I know that we have seen in the news, and you'll be seeing a lot in the news over the next years about the Rubin Observatory, the Vera Rubin Observatory, which is a new telescope that's been built in Chile, funded principally by the National Science Foundation, but also by the Department of Energy. That's kind of weird. Anyway, let me start talking about this telescope. Let me first start by just bringing us up to date on what's up this month, because there are a couple of interesting astronomical phenomena that are going to occur in the next month or so, and so I wanted to bring them up. The first thing is that full moon is coming up this weekend. It's on February 1st, and it's called the snow moon, and I guess we can understand why that is. If should it be clear tonight or tomorrow, which is highly unlikely, but if it is, go out an hour after sunset, and you should be able to see the growing moon. It's really getting quite large, quite getting to be full. It'll be near the small constellation of stars that we call the Pleiades or the Seven Sisters tonight, and then the moon moves among the stars, so it will be further away from the Pleiades tomorrow. But watch for the full moon. Watch in the early evening to see if you can see the moon. After we get past full moon, the moon will start rising later. The phenomenon that are interesting is on February 19th, Mercury will be at its greatest eastward elongation, which means it is furthest away from the sun, and it should be visible just after sunset towards the west. On February 28th, there is what we call a planetary alignment, which is where a bunch of the planets trace an arc across the sky. Not all of them are visible to the naked eye, of course. And the other thing, we'll take a look at that in a moment. The other thing that's interesting is that there will be a total lunar eclipse on March 3rd. It's visible from the western portion of North America, and I'll show you what we can see from Ithaca. It will just barely be visible on March 3rd. We'll be able to see it if you go to timeanddate.com. It will be visible early in the morning. At 6:04 a.m., the total eclipse begins, but then the moon sets. And so we will not be able to see the end of the total phase. But anyway, we'll talk about that again in February. As far as the planets are concerned, Mercury is really hard to see right now, but in another few weeks, it will be visible. Venus is bright and easy to spot in the west at sunset, although it's fairly low down on the horizon. Mars is invisible, basically. It's in the sun's glare. Forget it. Jupiter is really easy to see in the east-northeast now, and it's virtually visible all night. It moves across the sky, but it's visible all night. Saturn is visible low in the west at sunset, and it's fainter than Venus and Jupiter. As I mentioned, there's a planetary alignment. We had a planetary alignment a few years ago, which was really one that stretched across the sky. This one has a bunch of the planets all clustered up in the night sky, and then Jupiter is offset, and in this case, in this particular picture on around February 28th, the moon will be up too. Uranus and Neptune, of course, are not visible to the naked eye, but Saturn, Mercury, and Venus will be all close together. And so we'll see. We'll talk about that in February. That'll be around the time that I give another talk. Maybe it will be clear then. Who knows? Okay, so if we're going to talk about an observatory and a telescope and what we do with it, we have to remind ourselves why we bother to use telescopes anyway. And there are basically two things that a telescope does. Number one, it collects photons of light. And the bigger, it's like a telescope is like a light bucket. The bigger the telescope, the more light it can collect. So bigger is better in general. The other thing it does is that it allows us to see fine details or to see the difference between a fuzzy object and a nice clear object. This is actually a satellite trail. I'll come back and talk about that later. Um, so a bigger telescope gives us, in general, sharper images. It's also true that the sharpness of the image doesn't just depend on the size of the telescope. It depends on the wavelength of the light, but it also depends, if you're on the ground, of how much atmosphere there is above us, because the atmosphere causes perturbations in the waves of light traveling in and makes things fuzzier. But in general, we want to build bigger telescopes, and we want to put them on high mountaintops where the weather is clear and where there isn't much atmosphere above them. We would like to put them in space too, but sometimes that's too expensive. So what do we actually learn? We're going to be talking about what you learn from astronomical images. So what does an image tell you? An image gives you information about what the shape of the object is. So here we have some weird looking shapes. Here we have a very, very bright star, and I've mentioned this before. When you observe a really bright star with a telescope, you get this airy diffraction pattern, which is due to the telescope optics. And if the star is bright enough, you see this. In most stars, you don't see these streaks because the object just isn't bright enough and they are so faint you don't see them. We also have to keep in mind when we look at images, are we looking over a large part of the sky or are we looking over a small part of the sky? And so this is what I would call a wide field image. Here's Orion, the hunter. And this is the brightest star in the sky, Sirius. And this is it observed over a wide angle, or astronomers don't call it wide angle, we call it wide field. And so here we see bright objects in the wide field. Then if we go and we zoom in on that with a high resolution telescope or camera, we see more details. And instead of seeing these two stars, we might end up seeing that there are a whole bunch of other stars there. Here's an example of an image taken with a large telescope of Sirius. And when you look at Sirius with a large telescope, you notice that there's this little other object there. I hope you can see where my pointer is pointing. There's a little object that happens to be a stellar companion of Sirius, but instead of being this giant star significantly bigger than the sun, it's the size of the Earth and weighs more than the size of the sun. It's called a white dwarf, and we're going to talk about those sometime in the next couple of months. So what do you learn from images? You learn about the appearance and the structural details of objects. You can measure their position on the sky relative to other objects, other stars. And if you're able to measure their apparent brightness, and in particular their brightness with different filters centered at different wavelengths or colors, you can actually get a sense of the color of an object. So keep that in mind. Okay, so why is Rubin different from Hubble? Well, besides the fact that it's actually a larger telescope than HST and even larger than JWST, the most important thing from what we're talking about and the reason why Rubin is designed to be different is that it looks over a huge area of the sky at once. And HST and JWST, Webb and Hubble, are designed to take exquisitely sharp images, but of tiny patches of the sky. And Rubin instead is designed to look over a large area. So this shows you how much of the sky a single image of Hubble and Webb are, And this shows you the size covered on the sky of a single Rubin image. And that's the whole point. It's the wide field camera. And what it's designed to do is not have Martha observe tonight and Alan observe another night and David observe another night. It's designed to automatically scan the sky night after night after night after night. It can't cover the whole night, the whole sky in a single night, but it covers the whole sky in a few nights. And then to keep repeating that over and over and over and over again for 10 years, observing in 6 different filters of visual or optical light over and over again. And we're going to talk about what that lets you observe, what that teaches you. So another thing I think we should talk about is who was Vera Rubin? Why is this telescope named after Vera Rubin? Here's a Vera Rubin coin, which has just been issued. In fact, maybe you can go find one. It's a quarter, and it says Vera Rubin, and it says dark matter on it. And what Vera Rubin did was she measured the orbital speed of stars on the outer part of the Andromeda galaxy Messier 31. And we know how the planets orbit around the sun. And so people expected that maybe the stars in a galaxy would follow the same laws as we see in the solar system, which would be predicted if most of the mass was in the visible part of the galaxy. And once you got out towards the edge of the galaxy, in fact, the orbital speeds would fall. And what she discovered was that the stars in the outer part of the galaxy move faster than expected if all the mass was made up of stars. And therefore, even though the light ended, apparently the mass didn't end. And that was the first real direct evidence of the existence of dark matter. So that's recognized as being of significant interest that this telescope was named for her and that this coin has been issued. Okay, so astronomical images then. They teach us the position on the sky, the morphological appearance, and the apparent brightness. So here are 3 images of, they're faked, of course, a little bit, but of the same patch of the sky. What Rubin does is it keeps observing over and over and over and over again, and with different filters so that it can tell whether the object is blue or red, because it tells us something about color. So if you notice these 3 images, you will note these are images taken at different times. And so you have to look at the image and you have to say to yourself, okay, there are galaxies in the image, and there are stars, bright stars in the image, and there are faint stars in the image. You have to ask yourself, for any one of these sources, these objects, does it move? Maybe the motion is just due to the Earth's motion around the sun. Well, that would be easy. You'd see that that would have some effect over the period of a year. But maybe it moves in other ways. You also want to look to see if it changes size or shape. And maybe you see that from one night to the next, or maybe you see it over the period of 10 years. That's why it's being done for 10 years. And then you also want to see if it changes brightness. Again, as I said, if you take images with different filters at different wavelengths, you can actually measure the color of an object, which tells us something. So for stars, it tells us what the surface temperature of the star is. But we also have to keep in mind asking ourselves, what's the image's field of view? What's its angular resolution? What do we expect to see? We have to worry about whether it's sensitive to all kinds of light. And in particular for Rubin, we have to record when the image was taken. So I hope you've been staring at these images and you notice that there's a red object which moves. And there's a blue object which changes brightness. So that's the kind of thing that Rubin is going to find. So, as we've said, objects exhibit different morphologies. And Rubin will observe millions and millions and millions of objects. And for many of them, which are really, really far away, Rubin will see them as points of light. But for many, many others, they will have different shapes. And we need to understand what those shapes, where those shapes arise. We also know that objects exhibit different brightnesses. So I picked up a couple of images. Here's the one that I showed you of Sirius before. Not all stars have the same brightness. Brightness, I mean not only the apparent brightness, but the actual true luminosity. It turns out that Sirius A, the big star, which is hotter than the sun and bigger than the sun and more massive than the sun, is at the same distance as this little guy. In fact, they're at the same distance, but this one appears so much brighter than this one must just be a small object. And so we can learn about that. Then this one comes from one of the Webb deep fields. And again, different objects exhibit different brightnesses. They exhibit different brightnesses at different wavelengths and different filters. So some of them look red and some of them look blue. And here's the diffraction spike. This is from this telescope. The diffraction spike for Webb is more complicated. It has more angles, arrows here pointing out. So we want, Rubin will measure the brightnesses of millions of objects, hundreds of thousands for each image, over and over and over again. Okay, objects exhibit different colors. Again, you take images in different filters, you see, oh, this star is brighter in the blue filter than it is in the yellow filter, so it's blue, or vice versa. In general, here are two stars. Here's Orion, the constellation, with Orion the hunter. Here's his belt and here's his sword. The stars in the constellation have different colors. This is a galaxy, a pair of galaxies, but even with the pair of galaxies, you see that parts of the object are blue here and part is more orangey yellow. This is sort of gray and this is more whitish. We want to understand what it is that we're seeing. In general, for stars at least, blue tells us the object is hot. For red, it's more complicated. It generally means cooler, but it can also mean the object is dustier or further away. And so there's ambiguity there. But color teaches us things. I leave this for the last. I actually showed this in a class that I taught for one of my colleagues earlier today. And the group didn't know anything about anything, so I asked them what this was. And they noticed that it has a weird shape. Stars look like points of light because they're so far away and so relatively small compared to galaxies that we just see the point of light. This thing, though, doesn't look anything like these galaxies, and it appears black. It's not a black hole, though. It actually is a region that is so dusty, it has so much dust in it, that the starlight inside it or behind it, is completely blocked out from reaching us here at Earth. So we have to keep in mind that red tells us can be ambiguous. Our interpretation can be ambiguous. And David has his hand raised.
Can you tell us what dust is? Is it just broken up little particles of things?
It's broken up little particles. And it's not exactly like the dust that I find on my mantelpiece, but it is broken up little particles, mainly made of organics like carbon and silicon, and it's smaller than the dust on my mantelpiece, and it's out there in space, and you can't see it with the naked eye or with an optical telescope. Instead, what you see is an absence of the light behind it. Okay, another thing that Rubin will be able to do again, if you take images over long periods of time or short periods of time, you see that objects in the solar system, like comets or the planet Mars, appear to move with respect to the stars, which are very far away and don't appear to move. So again, you want to take a sequence of images over time and you can discover comets. Or if you watch Mars, this is an animation of the apparent retrograde motion of Mars over a period of weeks and months in 2003. Mars normally moves in this direction, but every now and then Mars loops back around in the other direction and then picks up. That was actually one of the motions that was noticed by the ancients, observing with their naked eyes, that convinced them that maybe the planets were orbiting the sun. Okay. Also, if you're very careful, I'm going to stop this one for a moment. If you're very careful and you look at these images, this was taken with Hubble, in a region of a nearby galaxy, there's a source here. I think you can see it changes its brightness. And now let's play this one where we're going to zoom in on a portion of the sky, so where they identify a bunch of sources which vary in brightness. You have to find one and see if you can see that we're going to zoom in on one in a moment. You'll see how it varies. I turned the sound off on this one, otherwise there's nice music playing in the background. But what astronomers do is Rubin will look at that whole area, and then it will try to find an object that varies ever so slightly. So this object actually is varying ever so slightly, and so are a bunch of the others. It turns out that there are a lot of stars that vary. So, in fact, we call stars variable stars, and they can vary on different time scales and for different reasons. So, there are stars that vary periodically. In other words, they brighten and then become fainter over a regular period of time, days, months, or years. If you observe and it brightens and it gets faint over a 10-day period, that repeats over and over and over again. We'll also talk in a moment about eclipsing binary stars, where you have two stars and one passes in front and then behind the other one. You see the light from the star that gets blocked out disappearing, and the two together appear fainter and then brighten again. We also talk about events that change brightness due to catastrophic cosmic events like supernova. We'll take a look at one of those. There are others which occur episodically or without a periodicity. Those include stars that we call novae as opposed to supernovae. This is not as bright an object as a supernova. And that's also a category of what we call cataclysmic variable stars. There's another phenomenon that we'll just take a look at now, where a star, if you're observing a star and that star has a planet, but you can't see the planet, but the fact that the planet is there may cause the star to brighten for a short period of time. And that is what we call gravitational microlensing. And it's due to the fact that light, when it passes by a foreground object, so here we have a star in the foreground which has a planet, and the white object is a star in the background. And if you are able to watch those stars over a period of years, you sometimes might see the combined image of the two stars suddenly brighten and then fade. And that is not because the star is blowing up or anything like that. It's because the foreground star had a little planet and it actually passed in front of the background star. Kind of cool. Okay. So, as I said, some aging stars vary in size. Let's look at this one first. Let me move it back to the beginning. We're going to watch a supernova explode. What do I mean by that? The star becomes hugely bright for a short period of time, blows off its outer envelope, and then maybe we don't see it anymore. On the other hand, there are other stars which, as part of their normal aging process, get indigestion and they don't burn their nuclear fuel as calmly and stably as a star like the sun. And when they do that, if I can replay it, yeah, okay. You'll see this star is normally burning its thermonuclear fuel, burning hydrogen into helium. But as it ages, its stomach doesn't work quite as well as it used to, and it starts to, in fact, change size and change brightness. And it does this with a regular variation or a regular period. So it pulsates. In fact, there's a category of star which was discovered in 1784 by John Ritchie, who discovered that a particular star, the fourth brightest star in the constellation of Cepheus, changes brightness periodically with a period of days, 10 or 20 days. If you watch it, it gets brighter, it gets fainter. It gets brighter, it gets fainter over and over again. In 1912, Henrietta Leavitt discovered that there's a relationship between the period of this variation for this kind of star that is similar to the bright star Delta Cepheus, which is visible with the naked eye. There's a relationship between the period of that pulsation and the mean luminosity of the star. And in fact, that relationship, the fact that if I observe the periodicity and I observe the apparent brightness, and I know this relation exists, if I have the luminosity and the apparent brightness, then I can figure out the distance to an object. And in 1923, Edwin Hubble found a variable star in the galaxy Andromeda, and he realized that this one star that he observed was a Delta Cepheid class star, and he used Henrietta Leavitt's relationship and realized that the Andromeda galaxy was very far away. It was millions of light years away, not in the backyard. So we want to find millions and millions of more Cepheid variables so we can measure distances. Oops. So the other case is the eclipsing binary star. And again, an eclipse is when one object passes behind the other one. In this case, the blue star has a mass 3.6 times the yellow star. The yellow star is smaller, the blue star is bigger. So when we observe the total brightness from the star, if the one star passes behind or in front of the other one, you either see more light or you see less light. And that will happen on a very cyclical pattern, but it's a change in brightness of the star as you observe it, an eclipse. Then another kind of star that proves to be episodic are called these novae. Supernova means a supernova. A nova means a new star. And what that generally means is that a star suddenly appears in the sky, a nova not being as bright as a supernova. They also are different phenomena. A supernova is really when a star completely explodes and destroys itself. A nova happens when you have two stars and they're orbiting around a common center of mass, but maybe some of the material of the companion star is pulled by the gravity of the the star that's going to be the nova, and material may be transferred from the companion star to what is going to be the nova. There are different kinds of nova, but one in particular, which is mentioned sometimes in the news, is a binary star system containing a white dwarf star, like that little teeny tiny faint star in Sirius. Remember that little teeny tiny one? It's a star called T Corona Borealis. It's a binary star system with a white dwarf. It's believed to be a nova. Um, After decades of some material from the big star falling onto the little star, there's a layer of gas that accumulates on the surface of the star. And if you get too much of that and it gets too dense, it can actually trigger thermonuclear fusion, and that causes a very strong brightening of the star for a short period of time. And that is what we see in this animation. So you've got a companion star over here. You have a white dwarf. Because remember, in this, it looks like everything is fixed, but everything is actually moving around. Too much material is dumped onto the atmosphere of the star. It doesn't destroy the whole star, but it causes to brighten for a period of weeks to months. So we think that all novae are binary star systems in which this mass transfer takes place. So we hope that Rubin will find lots of novae. So here's an animation of a supernova explosion. In a supernova explosion, the star actually implodes and blows itself up and throws out its outer envelopes. This is an animation of what we call the Crab Nebula. We know that the supernova was recorded by the ancients, or the not so ancients, in 1054 AD. The nebula itself was discovered in 1731. This was included in Messier's catalog as Messier 1 in 1758. It also contains a radio pulsar, which is the remnant of the star that exploded. The remnant is a tiny object the size of Manhattan, but it has more mass than the sun, and it is rotating on its axis 33 times per second. What we actually see with a small telescope, what we can see is this remnant. And if you observe it over the period of years, we are now able to actually watch this remnant expanding, which again tells us we think we know what we're talking about. Okay. I have to advance. Okay. Now, here's another example where we have two images taken at two different times. And so the question is, what do you see in the right image that you don't see in the left image? And so this is what Rubin's going to do. It's going to take images of the same part of the sky over and over and over and over again and look for things that don't look the same in different images. Obviously, it's not going to do that by having a wonderful group of people from Love Living at Home look at the images. It's all going to be done using sophisticated AI techniques. Does everybody see what's different? It's that, right? You do not see that in the left image, this one little star. It's right there, but it only shows up in the right image. That's a supernova, but it's in an object that's about 15 million light years away. This is a galaxy, the galaxy Messier 51, the whirlpool. Okay, a supernova. Okay, so let's talk a little bit about the telescope itself. So it is kind of a weird looking telescope, admittedly. We should say that the telescope is called the Simony telescope, but it's at the Vera Rubin Observatory. And it's an 8.4 meter diameter primary mirror. Hubble is 2.4 meters. Webb is 6 meters. This is 8.4 meters. It has a field of view of about 3.5 degrees, which is about 7 times the size of the moon, full moon. Every image covers that much. It's going to undertake over a 10-year period what's called the legacy survey of space and time. It takes all the data. The data get processed to take out instrumental and sky effects, and then all of the data are made public. It's located in Chile on Cerro Pachon at an elevation of about 8,800 feet. To remind those of you who've listened to me before, the Fred Young Similometer telescope will be at 18,400 feet, so 10,000 feet higher. But this is easy to get to. Why we do astronomy in Chile? We do astronomy in Chile because not only does Chile have some of the best astronomical sites in the world, the Chilean government has been very supportive. And so there are a whole bunch of telescopes. Um, this one will be located down in this part of Chile. The Fred Young Submillimeter telescope is located way up here in the higher mountainous region close to the Bolivian and Argentinian borders. But there are also a bunch of other observatories located in Chile. Here's a picture I like kind of the people standing with the 8.4 meter mirror. It's a big thing. It's huge. Um, and it's actually got 3 mirrors, as I'll show you in a moment. It uses 3 mirrors in order to be able to take the light and look over a large area of sky. The 8.4 meter mirror um, is special, and then there are 2 other mirrors. Another one that looks like the big one, um, and that makes they're specially designed to look over the wide area of sky, but also be a fairly compact structure optically, so that you can put it inside a dome. And then there's another mirror that allows you to capture the light from the first 2 mirrors and put it through that little donut hole that these people are sitting on. So we're going to take a look at first the animation, and then I'll look at different pieces of the animation that show that the light comes in from the sky and bounces off the 3 mirrors. So let's take a look at the animation, and then we'll go look at different segments. Light comes in from sky, bounces off 1 mirror, bounces to the second mirror, bounces to the third mirror, and then bounces back up to the camera. So let's look at that in pieces, because I had trouble following it, and I'm sure you did too. The light comes in from the sky and bounces off the primary mirror. It then gets reflected back up to the secondary mirror. So again, into the sky, up towards the secondary. In between the secondary mirror and the primary mirror, there are also a set of lenses that are put in place. So it bounces off, comes up to the secondary mirror, back down to the tertiary mirror, which looks like a depression. You see, there's a depression here in the primary mirror. That's the tertiary mirror. And then the light goes back up through the series of lenses and eventually hits the camera. So it's a very complex, weird telescope, which allows astronomers to look over this large area of sky while still building a big telescope in a small dome. Okay, so what is the legacy survey of space and time? I've explained the idea that we're looking for things that change. It will do wide area surveys, which have been very carefully designed to collect data and allow us to measure positions and morphologies and sizes and motions in a systematic, controlled, and repeatable way. It will observe repeated imaging of the night sky in six optical filters. It is expected that when images are processed and they're compared, the ones taken at different times and the ones taken in different colors, 100,000 events will be noticed of something that changes in the images taken on a single night. And the trick is going to be is to figure out which one of those is actually real, which one of them might be an artifact, which one of them might be somebody's satellite or an airplane or a bird or who knows what. The camera is made of 201 charge coupled devices, each one of which has 4096 by 4096 pixels, which is 3 gigapixels or 6 gigabytes per image covering 10 square degrees, which is 3,000 times the area of one Hubble Space Telescope image. It will overlap with a telescope called the Roman Space Telescope, which is supposed to launch in February in 2026 or 2027, which we will talk about when that happens. It doesn't take spectra, so it can't measure redshifts exactly, but it measures colors. It will measure the colors of all these objects. It will find objects that change brightness, find objects that change picture position, and it also allows you can take all of the images of a single spot of the sky and add them all up together, and you get to see faint objects. Okay. I just want to mention, maybe there are people who are interested in this. It will take one 6 gigabyte sky image in 15 seconds in one filter. It has to process that image, and then it starts taking another image within 20 seconds of the first one. And it does that over and over and over again. It will process about 100 million different sources in a single image pair. It has to catalog them and generate worldwide alerts if something interesting happens. It will generate 100,000 alerts per night, obtain 2,000 images per night, produce 30 terabytes of data per night, move the data from South America to the US daily, and it's going to repeat this for 10 years. So astronomers are going to be entirely buried in data, which means they better have powerful computers that can process this data for them. But needless to say, it's a big effort not only to store the data, archive it, and keep it, compare it. And so there's all sorts of development going on in database management, accessing the data, archiving the data, mining the data, et cetera, et cetera, et cetera. So there's another problem that I just want to mention, and that is that these low Earth orbit satellites produce to an image like what will be taken with the Rubin every time it takes an image. These low Earth orbit satellites reflect sunlight and they will be seen as streaks in all of the Rubin images, which doesn't make us very happy. What's really scary is this shows the number of satellites in low Earth orbit as a function of time. Here's 2019. You can start seeing we're increasing the number. And I just read that the Chinese are planning to put up a constellation of satellites, and it's expected by within the next few years, there will be um, almost a million of these satellites in low Earth orbit. It's terrifying. Now, hopefully, image processing can deal with this, but it's going to complicate the Rubin people a lot. Okay, so let's just take a quick look to finish up here. Here are two images of the same part of the sky, and I hope you can see this on your screen. I hope you can see that in this image, there are a few little streaks of green. Can you see those? Streaks of green, a streak of green, a streak of green, a streak of green, a streak of green. They're not visible in this image. Those are asteroids, objects in the solar system that are kilometers across, which are orbiting the sun. And Rubin, in the first look of images, discovered more than 2,100 of these. Here's another, I'm just going to show another couple of the Rubin first look images, which were released to the public a few months ago. Again, we have galaxies, we have interacting galaxies, we have bright stars, we have faint stars, we have nearby galaxies, we have distant galaxies. Each image is going to contain millions of sources that astronomers will analyze. This is just another one which I think is really pretty. This one is actually a combination of 678 separate images of the same part of the sky. They were obtained in more than 7 hours of observing. But again, if you keep adding data taken over and over again, most of the objects don't change. So they're there all the time. And it allows you to see much deeper and to get information on the color of objects. So where there's dark stuff and you don't see light, that's where the dust is. These dark patches tell you there's dust there. Okay, another thing, this little animation, which is going to start, I hope. There's a lot of stuff you can find on the web, obviously. It's just going to show us that they found a new asteroid. And if you watch over time, you see the asteroid move, whereas the distant objects in the background don't move. So we expect that Rubin is going to discover a lot of asteroids. And here's another one. This is actually a collection, a zoom in and zoom out of 1,100 images, starting with a close-up of a spiral galaxy, and then it zooms out, and you're going to end up seeing in the image that we see at the end, we would go in and we would find that there are 10 million galaxies in that image at the end. What we expect to find over the course of the 10 years of the survey is about 100,000 near-Earth asteroids. Those are asteroids that come into the inner part of the solar system close to the Earth. We expect to find 10,000 new comets, maybe 50 what are called interstellar objects, which are small objects like asteroids or comets, but which come from outside the solar system. And maybe we'll find Planet 9. We'll find millions of variable stars, millions of novae. We hope to find 4 million supernovae and 20 billion galaxies. And so I'm going to stop there. Needless to say, there's lots more to come, and I'm sure over the next years you're going to see a lot of. I'm going to stop sharing. We'll see a lot of these different kinds of weird objects. And of course, what we're really interested in finding is the stuff that we discovered that I don't know how to describe to you yet because I don't even know it exists. Anyway, let me stop there and see if there are questions. And you can rate you are all muted, so if you want to speak, you will have to unmute yourself. And you can raise your hand any way you want to, because I can see everybody who has their camera on. So the way this is going to work is there are different people who have applied to have access to the data to look for asteroids or to look for supernovae. But all the data will be public. The problem is that the data sets are gigantic. And most people can't really access them without access to a supercomputer. Charlie.
That was my question. Is it going to be all the data stored centrally someplace?
Yes. All the data will be stored centrally someplace. And there are people who are on the Rubin team who, for example, there are huge working groups. I'm in fact associated with one of the working groups that must have 400 people on it.
Wow.
And I'm not really interested in looking at the raw data. I want to know when they find 500 supernovae. When they get to 500, it becomes of interest to me because I want to know something about the distance to those objects. Having one doesn't do me any good. Having 500 would be worthwhile, which means that the people in my subgroup who are in the working group, we're not going to get any results for 5 or 10 years.
Yeah. Yeah.
But there are other people who want to study supernovae as they go off. And so they have access to the data, and the National Science Foundation supports these groups to access the data. And there's also support for the group that will have access to the raw data that are associated with the Rubin Observatory. David?
How will um, how will you evaluate publications that use these data?
You're a really good question. So all of that has been negotiated in advance. And for every working group, there are discussions that people have been discussing this for years and years and years. You have rules for who can publish, who gets to be the first author.
Really?
And this is like high energy particle physics. As I said, in the working group that I'm on, there are maybe 300 people. I'm not going to expect to have my name on any paper except a paper. Well, I probably won't have my name on any paper because if it's 10 years from now, I'm hoping to be knitting a new scarf, not analyzing these data. But somebody else will be analyzing data, and the person who does all the work to do the analysis of the data which has already been processed will be the first author. But there are huge pages and pages of these rules. But they've been agreed to in advance. And because people have thought about how you're going to do this without getting people mad. Lorene?
Yeah, on the list of items or things that oops, sorry, wait a second. On the list of things that you might see or find, you mentioned artifacts, and I was just wondering what you consider an artifact.
Well, so like those diffraction spikes that you see, those can be artifacts. Okay, also, you have this big 8.4 meter mirror. Well, what happens if a few particles of dust floating in the air end up on a piece of the mirror? That can cause a slight blemish in an image. Um, uh, and so you could get a blemish in an image caused by uh, something that falls onto the mirror. You might have a little bit of a problem. You will have problems due to airplanes flying through. Maybe it's something that's so faint you don't really notice it, but it's not a cosmic object.
Got it.
Um, and so that has to be that has to all be taken into account. There will be 100,000 alerts per night. We think these two images don't look exactly the same, but maybe that's because there was a cloud in the way.
Mm.
And so it's a huge data processing challenge. John, you're muted.
Is there any procedure for cleaning the mirror?
Yeah, you have to go in and clean these mirrors um, probably once a year. So there's going to be a period of time probably when the weather is expected to be not so good, where they'll shut the telescope down and clean the mirror. I don't know if they're going to clean it every year. Maybe they clean it every other year. You have to do that because even though you have it in a dome at night, during the day, at night there is dust blowing around. There will be birds that fly over and do bad things. You will want to clean it sometime over the course of the 10 years. So it's pretty exciting, and it's also a huge it's a huge data processing challenge where you've got to train your computer program to look through these different images and sort through the millions of objects and figure out which ones are actually interesting. And even then, some people like asteroids that move. Other people find asteroids really annoying because they get in the way of their favorite star for a short period of time. So, different people will be tweaking the software that analyzes the different images to find the objects that they're interested in. But that's what's going to keep astronomers busy for a while. And so we'll watch over the next weeks, months, years. I'm sure there will be exciting things that are discovered, and maybe now you know a little bit about it. Okay. Anyway, that's what it was all about today, folks, and see you again in a month or so.
Thank you so much, Martha. It really was exciting and interesting.
It's going to be, as I said, the most exciting thing will be what I didn't talk about and don't even know about that someone will discover. Maybe we'll find Planet 9. Okay, we'll see you in a month.
Thank you.
Stay warm.
We'll approve the data center out here in Lansing if it can be used for astronomy.
Yeah, okay, good deal. I don't think that's part of the plan, but good idea, David. Okay, see you all later. Bye-bye.
Bye-bye.